Welcome to the segment on temperature-dependent output for photovoltaic systems. In this lesson, we'll learn how to calculate the output voltage for photovoltaic modules and arrays based upon temperatures that deviate from standard temperature conditions. Let's begin by looking at what happens to voltage when temperatures are higher or lower than STC conditions. As a rule, output voltage will always decrease with increasing temperature, and output voltage will always increase with decreasing temperature. Practically, this means that under cold weather conditions, we'll always have a higher voltage, which could be a concern for safety. However, under hot weather conditions, we'll always have a lower voltage, which could be a concern for inverter turn-on and output. There are two ways that we'll learn how to calculate the voltage under non-STC conditions. One is by looking at the listed voltage temperature coefficient, and the other is looking at the percent voltage change from STC. As a reminder, all photovoltaic systems are rated under STC, or standard test conditions, which are defined as 1,000 watts per square meter at 25 degrees Celsius and an air mass of 1.5. Under these conditions, open circuit voltage and maximum power voltage are defined and fixed. Any changes from those temperature conditions will result in a change in voltage. Luckily for us, voltage temperature coefficients are listed by module manufacturers and allow us to calculate this change. For silicon, those coefficients tend to be around -2 millivolts per degree Celsius, or 0.002 volts per degree Celsius. This is a value per individual silicon cell. However, there are multiple cells in a module and numerous modules in an array. So while the voltage change may seem fairly low for a single cell, it results in a significant deviation from STC ratings for an array. Let's begin by looking at the mathematical formula used to predict the voltage at a given temperature. In this case, we'll start with looking at cold temperature conditions. This is important for safety reasons again, because voltage can increase significantly when it's very cold outside. This can damage equipment and cause a fire. In general, we start with the voltage at STC for our voltage of interest, either the open circuit voltage or the maximum power voltage. If we have cold, low sun conditions, such as a very cold, clear winter morning, this will be just enough to generate a voltage in the photovoltaic, but no current. That's identical to open circuit voltage conditions. So to calculate the real voltage, we'll need to combine the open circuit voltage at standard test conditions with the voltage calculated by the voltage temperature coefficient at a temperature of interest. So how do we get that temperature of interest? Well, we need the maximum low temperature ever recorded for that location where the array will be placed. This is most easily found by consulting online resources for weather and climate. In the United States, we could use NOAA, or the National Oceanographic and Atmospheric Administration, or online commercial sources to get these data. Also note that we must always work in the temperature units given by the cell manufacturer, which are typically Celsius or Kelvin. Once we know the maximum low temperature, we have to look at the specifications for an individual photovoltaic module. Let's suppose we have a module where the open circuit voltage is listed as 64.9 volts, and it has a temperature coefficient of -0.175 volts per degree Celsius. Let's then put this in a location where the lowest recorded temperature is -20 degrees Celsius, which is quite cold. We would first subtract the STC 25 degrees Celsius from the -20 degrees Celsius temperature of interest to give -45 degrees Celsius, which is the deviation in temperature from STC. We then multiply that value of -45 degrees Celsius by the temperature coefficient of -0.175 volts per degree Celsius, which gives us a product of 7.875 volts, which is the voltage deviation from STC. Summing the 7.875 volt deviation with the 64.9 volts at STC gives us a new voltage of 72.78 volts, which is higher than the STC voltage for VOC conditions. This makes sense because, as we just discussed, voltage will increase when the temperature decreases from STC conditions. Now let's do the calculation for warm weather conditions. The calculation is very similar, but we have to think about when warm weather conditions actually occur. Well, this is going to be typically during the summer at the highest point of the day, so the module is outputting a maximum power and thus a maximum voltage. So in this case, we'll be looking at the voltage at maximum power, or VMP, instead of the VOC. In this calculation, we don't have to look at the maximum high temperature ever recorded because we aren't concerned about safety associated with high voltages. High temperatures mean low voltages, so we're looking at the minimum voltage that we could expect under full sunlight operating conditions. This will impact things such as the turn-on voltage for the inverter, but not safety. Consider a location where the average high is 29 degrees Celsius. That's the ambient air temperature, but we also need to consider what happens when a module is on a rooftop. The National Electric Code in the United States and accepted international standards for rooftop temperatures is 30 degrees Celsius above the ambient air temperature. This means we would sum 29 degrees Celsius ambient air temp with the 30 degrees Celsius rooftop adder to give an operating temperature of 59 degrees Celsius on the roof. Looking at model specifications, the maximum power voltage will always be lower than the open circuit voltage. In this case, the maximum power voltage is 54.7 volts at STC. So we would subtract the STC 25 degrees from the 59 degree rooftop temperature, which gives us 34 degrees Celsius. We then multiply that temperature by the temperature coefficient of negative 0.175 volts per degree Celsius. The product, negative 5.95 volts, is then added to the maximum power voltage at STC, and we get a new voltage of 48.75 volts. Notice that this voltage is under warm conditions, meaning that the operating voltage is actually lower than under STC conditions. When considering the voltage under warm weather conditions, 30 degrees Celsius is not always the best value to choose when designing system temperatures. Deviations from that value will be based upon empirical data that you can find online for temperatures and combining that with the National Electric Code or other sources. Suffice to say, the further away from the rooftop, the lower the temperature adder will be. We'll come back to this again when we do site-based design in the next course.